Hi GOH, this is Unit 2, Lesson 10, Congruence Reasoning about Triangles. So this is the last lesson in this unit, and it sort of ties it together, and it's an introduction to what we're going to do in the next unit, which is proving that triangles are congruent to each other. So two triangles would be congruent if they have the same size and shape. We can now say, given our study of rigid motions, here's what's going to be true about triangle congruence. Two triangles in a plane are congruent if a sequence of rigid motions can be found that make the vertices of one triangle coincide with the vertices of the other. That means that they lie on top of each other. So in the diagram we have for exercise 1, we know that BD is perpendicular to AC. If BD is perpendicular to AC, and there's a C out here that sort of got cut, that got cut off, and now we lost our page there. Okay, so there's our C. If it's perpendicular, then that means it forms a right angle. And AD, which is this left side, is congruent to CD. All right? Prove that my triangles are congruent to each other. Now we're going to do a more formal proof that will be a little bit different in the next chapter. But you can see that if this is a right angle on the right, it's also a right angle on the left. They also have this side is congruent to this side. And they also share this side in the middle right there. So they have two sides of this triangle and the angle between it, and two sides of this triangle and the angle between them are congruent. But that's something more for the next chapter. Based on the givens in the diagram, what rigid motion do you think will be used to map triangle BDC onto triangle BDA? Try this transformation with tracing paper. So we don't need to use tracing paper. But basically, how did this triangle BDC, this triangle on the right, map onto this triangle on the left? Did I do a translation, a reflection, a rotation? What did I do? And remember, we can sort of look at the order of the letters, like look at the C and look at the A. Those correspond to each other. So C matches up with A. And then I can look at the B. B is the first letter, so is B. B matches up onto itself. And my next letter, D, matches up to itself. So the B and D did not move at all, but the C mapped onto A. Well, that sort of indicates to us that I must have done a reflection. So I did a reflection of triangle BDC. Now I always want to say what I reflected it across, and it's always going to be a line. I reflected triangle BDC across segment BD. Now prove using rigid motions that my triangles are congruent to each other. And I left out my triangle symbol right there. But basically I reflected BDC across BD, and what happens? The B and D get mapped to themselves. That's because they're on the line of reflection. Right, so the B maps to B, the D maps to B. They map to themselves. They're on the line of reflection. The C maps to A because, now the reason why it maps to A is because BD is perpendicular and it's also a bisector. It's a perpendicular bisector. Now how do I know it's a bisector? This is a bisector because this left half was equal to this right half. So it's a perpendicular bisector of AC. Since all three vertices, of BD, triangle BDC, map to triangle BDA using a rigid motion, and the rigid motion, remember, was a reflection, the two triangles are congruent. I left out triangles. The two triangles are congruent to each other. All right. Exercise 2. So in the diagram, we know the following. We know that ACD and BCE are lines. C is the midpoint of both AD, so it's a midpoint of AD. It cuts AD in half, and also C is the midpoint of BE. So all of those segments are congruent. I also have these vertical angles that are congruent to each other. So basically I have the two sides and the angle of one triangle and the two sides and the angle of another triangle are congruent. What's the rigid motion? Well, let's look at the order of these letters. I have A maps to D. So the A maps all the way over here to D. The B maps to E. And the C maps onto itself. So I didn't do a reflection. This time I rotated triangle ABC. Now we want to say how much I rotated. So I rotated triangle ABC 180 degrees. And what did I rotate it about? I rotated about point C. That's why C mapped to itself. So basically A maps to D. B maps to E. And you can see that by the colors. And C maps to itself. Since all three vertices of triangle ABC map to the three vertices of triangle DEC using a rigid motion, then the triangles are congruent. So since all three vertices of triangle ABC map to the three vertices of triangle DEC using a rigid motion, that part's important, and the rigid motion this time was a rotation of 180 degrees, then the two triangles, oops, I left out triangles again. The two triangles are congruent. Remember, a rotation is a rigid motion. It preserves the length and it preserves the angle measure. All right, next page. These transformational geometry proofs can be challenging even in fairly simple situations. So in the following diagram, it is known that AB bisects angle CAD. So it's taking angle CAD, this whole angle, and it's cutting it in half. So this top half is equal to this bottom half. And I'm also bisecting angle CBD on the other side is being bisected. So this top half is congruent to this bottom angle right there. This will be enough using rigid motions to show that triangle ACB is congruent to triangle ADB, because they not only have the two angles that are congruent, but they also share that side in the middle. What angle pairs must be congruent to each other? Based on what's known, explain, and mark them. So I've already marked them, but basically angle CAB is congruent to angle DAB, and angle CBA is congruent to angle DBA. Remember, I'm using the three letters. When we do actual proofs, you'll be able to put numbers in there and it'll be a little bit easier. The reason that I know they're congruent is because an angle bisector, so this is sort of getting ready for doing our proofs in the next chapter. An angle bisector divides an angle into two congruent angles. All right, so that's how I know those angles are congruent. If triangle ADB, now that's the one on the bottom, was reflected over this line AB, what 2 points would not move? We call them fixed points. And why would they not move? Well, the 2 points that are not going to move, if I reflected triangle ADB on the bottom, the A is not moving and the B is not moving. The reason why they're not moving, we've said this before, they're on the line of reflection. If triangle ADB was reflected in AB, why must the image of point D, i.e. D prime, fall on both rays AC and BC? The image of D must fall on AC and BC because of the angle pairs equal in part A. So basically, this point D, if I reflect it, has to fall on this ray, and the rays meet at C. So ultimately, it's going to fall on point C because of these angle pairs being congruent to each other in part A. So the image, and don't worry, the proofs will not be as complicated as this. The image of D must fall on AC and BC because of the angle pairs equal in part A. Since D prime must fall on AC and BC, where does it tell you that it must lie? And we've already said that. The image of point D must fall on point C. Because C is the only point on both AC and BC. It's sort of where AC and BC meet, so it has to fall on that point. Explain why we now know that the triangles are congruent. Because a reflection, which happens to be a rigid motion, a reflection has mapped all three vertices of one triangle to the three vertices of the other. And remember, this is the important part, a reflection is a rigid motion. It preserves length and angle measure. Preserves length and angle measure. On the regions, you will absolutely have a question that is going to deal with rigid motion and the fact that it preserves length and angle measure. All right, last problem. Given that line R is the perpendicular bisector of BC and AD, which of the following would be used to prove that ABE is congruent to DCE? So basically, I'm trying to prove, and let me just highlight these. Let me get a bigger marker. I'm trying to prove that triangle ABE, which is this guy all the way here, is congruent to this guy over there. Here's what I know. I know R is a perpendicular bisector of BC. It's a bisector of BC. It's cutting BC in half. So I know that those two are congruent to each other. And let's read through my choices here. It's also perpendicular, so I know this. And is it also the perpendicular? Oh, it's also the perpendicular bisector down here of AD. All right, so did I do a reflection of ABE across the line AD? So AD is down here. Okay, if I reflected it across line AD, it sort of would have been down here, not over there. Did I do a 180-degree rotation of ABE about point E? If I did that, then the image would have been up here somewhere, like up there, which it wasn't. All right. Did I do a translation of ABE in the direction of BC? A translation is just a shift or a slide. Notice that this has been like flipped over. So let's look at choice 4, which happens to be the answer. I did a reflection of ABE across line R. So basically, I took ABE and I reflected it over line R, and it resulted in here because the B maps to the C, the A maps to D, and E maps to itself because it's on the line of reflection. All three vertices of triangle ABC map to all three vertices of triangle DCE. Okay, so that was the last lesson in this unit. We're going to practice that tomorrow, and then we'll do some review.